Welcome to This Explainer. Today we're taking a seriously complex fluid dynamics problem and exploring how mathematical precision is basically the only thing standing between a smooth operation and a multi-thousand-dollar piece of heavy machinery just tearing itself to shreds. We're going to break down the exact physics of fluid flow, pipe friction, and pressure limits to solve a very real-world problem. It's like a giant puzzle, and we're going to solve it together. Let's hook right into our mystery here. Can water actually boil at room temperature? Well, the surprising answer is absolutely yes. See, if the pressure inside a pipe drops way too fast, water can undergo a phase change and literally boil cold. This creates these tiny, highly explosive vapor bubbles. And when those bubbles hit a high-pressure zone, they collapse with immense force, generating shockwaves that can bite actual chunks of metal right out of a pump impeller. This destructive little villain is known in the engineering world as cavitation. Section 1. The threat of cavitation. Predicting the danger. To defeat this silent mechanical killer, we have to predict where it strikes before it happens, right? Cavitation isn't just bad luck. It's a completely predictable physical phenomenon governed by pressure and temperature. Let's look at the specific setup we're trying to protect today. Looking at this physical system, you can clearly track the fluid's journey. It starts from point 1, way up at the top surface of the open reservoir, flows down through the gravity-fed inlet piping system, passes through a control valve, and heads right into the suction side of the pump at point 2. Now that second point, right at the pump inlet, that's our danger zone. That is exactly where the pressure is going to be at its absolute lowest, making it the prime spot for cavitation to strike.
Section 2. Mapping the system to find our maximum flow rate limit.
Our specific mission for this explainer is to calculate the absolute maximum flow rate for pumping standard 25 degrees Celsius water through this exact setup before cavitation destroys our pump. To pull that off, we need a metric to measure our safety margin, and that metric is NPSH, or Net Positive Section Head. This acronym is basically our ultimate detective tool. Think of NPSH as a vital safety buffer of pressure. The pump manufacturer tells us how much pressure the pump requires to function without cavitating. That's the required NPSH. Our job as system engineers is to figure out the available NPSH based on our specific piping and reservoir setup. So the crucial takeaway here is this. As long as our available NPSH stays higher than the pump's required NPSH, our machinery is totally safe. The exact moment they equal out, that's when the bubbles form and the destruction begins. Section 3. Decoding math using the Bernoulli equation. Now let's grab our math tools and translate the totally intimidating Bernoulli energy equation into physical reality. Bernoulli's equation is essentially a ledger of energy. It tracks pressure, velocity, and elevation as the fluid moves from the reservoir to the pump. But good news, we really don't need the whole messy ledger. We can simplify it dramatically just by looking at our physical setup. Step 1, start with the full formula. Step 2, look at point 1, the surface of that massive reservoir. The water level there drops so slowly that the velocity is practically zero. So, boom, we cross that out. We also cross out the pump head because we're measuring the pressure right before the pump actually does its work. Step 3, since the reservoir is open to the air, our starting pressure is simply atmospheric pressure. So by crossing out all those variables that just equal zero in our specific system, we're left with a highly focused, practical formula for our available NPSH. But hey, we can't ignore the real world. We also have to account for head loss, noted as HL. This is the energy literally stolen by friction as the water scrapes along the inside of the pipes and as it forces its way through elbows and valves. In our system, the combination of these pipe fittings and the valve gives us a loss coefficient of 7.4. That friction just eats our energy, directly dropping our pressure at the pump inlet and chewing right into our critical safety buffer. So let's see how this all builds up when we run a test scenario. If we run a theoretical test at a flow rate of 400 gallons per minute, we can plug our exact physical dimensions directly into our new simplified equation. We've got a pipe diameter of 4 inches, or exactly 0.1016 meters. Pushing 400 gallons a minute through that specific pipe gives the water velocity of 3.112 meters per second. We also have a helpful 4-foot gravity drop from the reservoir to the pump, which gives us some free pressure. And based on our Reynolds number, we get a pipe friction factor of 0.0306. When we take all of those specific test variables, plug them into our NPSH equation, and subtract the vapor pressure of 25-degree water, crunching those numbers gives us an available NPH of 7.148 meters, which is roughly 23.5 feet. So what does this tell us? It means that at 400 gallons per minute, we've got a very healthy, very safe pressure buffer. To put that into perspective, a standard industrial pump in this setup might only require an NPH of 5 to 10 feet to operate safely. So sitting way up at 23.5 feet means we have plenty of clearance. The pump is perfectly happy, and cavitation is nowhere in sight. Section 4. Hitting the limit and finding our maximum safe velocity. Well, 400 gallons per minute is just a comfortable test run, right? Out in the industry, time is money, and we want to pump as fast as physically possible. We really want to find the absolute breaking point where the available NPSH exactly matches the required NPSH, closing that safety buffer completely to zero. When we balance the equation and solve for the maximum velocity, the math reveals a pretty dramatic payoff. At 25 degrees Celsius, the absolute maximum limit before the pump starts destroying itself is exactly 600 gallons per minute. If you push that system to 601 gallons per minute, the increased velocity creates too much friction, the pressure at the inlet drops below the water's vapor pressure, and those destructive boiling bubbles immediately begin to form. 600 is our hard, undeniable speed limit. Moving to our final section, Section 5, turning up the heat and exploring temperature effects. Just when we think we've completely solved the mystery and optimized our factory floor, we get a major plot twist. Engineering environments rarely just stay perfectly at room temperature. Let's compare our initial room temperature state of 25 degrees with a much, much hotter 60 degrees Celsius scenario. We need to see exactly how heat rewrites the rules of fluid dynamics and messes with our carefully balanced equations. The core thermodynamic principle here is absolutely fascinating. As water gets hotter, the pressure at which it wants to turn into vapor completely skyrockets. Hotter water is incredibly eager to boil. In our NPSH equation, vapor pressure is a negative. It subtracts directly from our available safety buffer. So as that vapor pressure climbs with the heat, our safety net rapidly shrinks. This creates a cascading chain reaction in the physics of the system. Think about it. When temperature goes up, vapor pressure goes up. Simultaneously, the higher heat causes the fluid's density, its physical heaviness, and its viscosity, its thickness, to go down. Now, these shifts might seem kind of minor on their own, but together, they pull the rug right out from under our pressure buffer, ultimately shrinking our critical available NPSH. Visualizing this consequence, we see the harsh reality of hot water pumping. Running the exact same system with 60-degree water instead of 25-degree water drops our maximum safe flow rate from 600 gallons per minute down to 555 gallons per minute. That temperature shift is costing us 45 units of pumping capacity every single minute. If an operator didn't know the math and tried to push 60-degree water at that old 600-gallon per minute speed limit, the pump would instantly suffer massive cavitation and basically tear itself apart. Which brings us to our ultimate takeaway. If a relatively modest 35-degree shift in temperature costs us 45 gallons per minute of productivity just to avoid mechanical destruction, what in the world happens to pumps operating in extreme industrial environments, like nuclear reactors or chemical refineries? I'll leave you with this final thought. Understanding this fluid math, mapping the friction, and respecting the vapor pressure isn't just some academic exercise on a whiteboard. It is literally the only thing standing between extreme industrial environments and catastrophic mechanical failure. Keep that in mind the next time you turn on a tap or hear an industrial pump humming safely away.